We have at least two strategies for finding conditional probabilities. First, we can use the conditional probability formula. The probability of A given B is the probability of A and B divided by the probability of B. We could use a contingency table, or we could use a tree diagram. You should use whichever is easiest. For example, suppose a machine has two parts labeled A and B. The probability that A works for a year is 0.8, and the probability B works for a year is 0.6. The probability at least one part works for a year is 0.9. Calculate the probability that part B works for a year given that part A works for a year. We'll let A be the event that part A works for a year, and B the event that part B works for a year. Note that one part works for a year if either part A works for a year or part B works for a year. So this event is the union A union B. Now, a useful strategy is to don't answer the question, answer all questions. We're given two probabilities in the probability of a union, and we know the probabilities of two events and their union are related by a formula. We know the individual probabilities and the probability of their union, so we can substitute those in. And then that tells us the probability of their intersection. Well, we don't actually want that. We want a conditional probability, but our conditional probability formula does require this probability of an intersection, and so we can compute the probability that B works for a year given that A works for a year. That's the probability of their intersection divided by the probability of the conditioning event. And again, if you really want to understand the subject, solve it again. Find a different solution. So let's use some version of our 10,000 table. Since our values are given to one decimal place, we can model what happens when 100 machines are considered. So we'll set up our contingency table. A either works or it doesn't. B either works or it doesn't. The probability that A works for a year is 0.8, so we'd expect A, the event, to occur a total of 80 times and to not occur the remaining 20 times. The probability that B works for a year is 0.6, and so that tells us we'd expect B to occur about 60% of the time and to not occur the remaining 40% of the time. Now, there are three situations where at least one part works for a year. Either A works for a year and B works for a year. That's this box. A works for a year but B does not. That's this box. And B works for a year but A does not. And that's this empty box. Now, notice these two boxes correspond to A working for a year. So there's really two cases of importance. Either A works for a year, or A does not, but B does. And we know that A works for a year in 80 of the cases. So 80 of the cases have to be in these two boxes, and that means the remaining 10 cases must be in this box. And again, don't answer the question, answer all questions. Since we know the sum of the entries in this row, we can find the remaining entries in the row. And since we know the sum of the entries in these columns, we can find the remaining entries in the rest of the table. Now, there is a question in this problem, and we're given that A works for a year. So we know we're in this column, and we want the probability that B also works for a year. And so we see that of the 80 times part A works for a year, part B works for a year in 50 of those times. So our conditional probability is... Now, part of the reason it's useful to do this problem twice in two different methods is that our answers, if they're correct, should actually agree with each other. And in this case, we get the same answer no matter how we solved it, so our answer is probably correct. We could also use a tree or a path diagram. So our first branch, well, let's make that either A works for a year or it doesn't. And then our second branch is either that B works for a year or it doesn't. However, note that the probabilities we need for those second branches are the conditional probabilities. For example, here we would need the probability B works or doesn't work given that A has worked. And we don't have those probabilities. While we could find them, it would take some effort, and so this method is probably not the best approach. And that's an important observation. If we only knew how to solve this problem using tree diagrams, we would have to use that approach no matter how hard it would make the problem. But if we have multiple ways to solve a problem, we can switch if it seems like the current method is going to take too much work.